We have just learned that distribution of frequencies is an important tool, especially when you visualize it, because it shows you the shape of your data, right? So the density of your data. It has one additional drawback. Even if your sample size is large, in my case, in this case that you see on the slide, it says 100 values. So we have 100 apples, sugar content of 100 apples. And then, of course, if you change the number of beans, in this case, it doesn't influence the shape much. You can see it clearly. However, look at the scale of y-axis. You can see that the more beans you have, the smaller and smaller and smaller the frequency becomes. And that's kind of understandable, because if you have more beans, the size of the bean is smaller. And therefore, the chance that you will have a lot of values within these beans is also smaller, right? So you will have the number of counts will get lower and lower and lower. And you can clearly see it here, where I just simply have the same scale. So I set the same scale between 0 and 40. It's just a count, it's a frequency. And then you can see that the distribution shape gets flatter and flatter and flatter. So it goes down and down and down. So that leads to two kind of problems. First of all, you cannot compare distributions directly. For example, if you have sample of different size, or if you use distributions of different beans, you cannot compare them because shape will be different. Can we make it independent on the sample size and the number of beans? Well, in fact, we can, but let me show you the intuition first. So again, you can see that here we have two distributions made for the same sample of 100 values. On the top, you can see it's 4 beans, and on the bottom, you can see it's 8 beans. These are corresponding frequency tables. So this is a frequency table for 4 beans, and this is a frequency table for 8 beans. And now you can see, for example, so why this, for example, bar looks like it's shown here. Because the relative frequency is 0.12. So it means that 12% of the values are within this interval, within this bean. And you can see that the left boundary of this bean is 8.8 weight percent, and then the right part is 9.3 weight percent, right? So it means that the size of this bean is 0.5. That's exactly 9.3 minus 8.8. It gives you 0.5, right? So this is the size of this bean. Now, if we use 8 beans, then the size of every bean is twice smaller. So for example, in this case, we have 4% of the values in the first bean, and 8% of the values inside the second bean. But why? Because the bean is also twice smaller. Now we have 0.25 and 0.25 here, because we took the original bean that we have here, yeah, and then we split it, we halfen it. So we have half here and half here. So that's why actually this percentage is going down. You can also see it visually here. If I overlap these two plots, you can clearly see that this, if I put these two beans here, you can see that every bean is smaller. Every bean is smaller. What we can do, how we can solve this problem? Well, we can compute the percentage of values per unit. For example, in this case, we can compute how many values, the percentage of values we have per 1 weight percent. In this case, you can see it will be 24%. And if you compute this for the other two beans, you will find out that it's 16% and 32%. So this value is a little bit smaller than this one, while this value is a little bit larger than this one. Let me give you an extra intuition about these calculations. The idea is following. Imagine that you have 8 persons in this room. So we have a room 10 by 10, so it's 100 square meters. And then we have 8 persons in this room. So we can say that we have 8 persons in 100 square meters. Now imagine that we split this room into 2. And now the persons look like this. So we have 2 rooms instead of 1. The overall area of these 2 rooms together is the same. It's 100 square meters. But the area of every single room is smaller now. So now we have 50 square meters in the first room and 50 square meters in the second room, right? The overall comfort of these persons, of course, we didn't change it. But apparently we have less persons in room number 1 than in room number 2. So we can say that for room number 1, persons feel a little bit more comfortable. They have a little bit more space. While in room number 2, persons are a little bit more crowded. So we have less space per person. Right? How we can quantify this comfort, how much room every person has? We simply can compute a density, right? So we can compute how many persons we have per 1 square meter. So if we do it for the first room, we have 0.08. If we do it for the second case, we have 0.06 for room number 1, and then we have 0.10 for room number 2, right? And then you can see that actually here, the 0.08, it's simply average of these two values, right? So the overall comfort is the same, but now if we split this into two rooms, we can see that this a little bit less dense and this is a little bit more crowded, more dense. So that's exactly what is called density. So we can compute density by simply dividing number or percentage of values that we have to the size of the interval. Now let's implement it here. So we have, again, we have the percentage of the values. So here we have 0.12, so it means 12% of the values within 0.5 weight%. So how to compute density? We simply take 0.12, divide it to the 0.5, and that gives you 0.24. And this means that you have 24% of the values in 1 weight% of inside this interval, right? So this is the density, how dense the values are. And then we simply can compute it for the other bins. You can see that the density is going, the highest density you have here, and then this is the two intervals where you have the lower density. Similarly, we can compute it for the other table. In this case, the bin width is 0.25. For example, here you have 16, which is a little bit larger than 24. Here you have 32, smaller. This one is smaller, this one is larger. But what is 24? It's exactly average of these two values. So we didn't change the overall density, right? So the overall density is the same as 24, but now if you split it, of course, the individual densities will be a little bit different. Now, if we visualize this as density distribution, you can see that in this case, the overall shape is more or less the same. Of course, we have more details when we use 8 bins compared to 4 bins. But now you can see the height of the bar and the overall area of this distribution histogram is the same. And now if you compare these two bars with the original bar, you can see that this bar is a little bit higher, this bar is a little bit lower. And then if you take average height of these two bars, you will get exactly this bar. So by reducing number of bins, you're simply averaging the original histogram. So that's the basic idea. So density distribution can be computed by taking relative frequency and dividing to the bin size. What else is important? Well, like in frequency distribution, the width of the bin, the width of this bar, when we represent the density distribution as a bar plot, is the same. It's the width of the interval, right? But the height is density. But what does it mean? If height is density and if width is bin, the area, if we compute area of this bin, will be the relative frequency. So the relative frequency is the area of every bin. But what it means? It means that if we take the total area, so if we compute area of every bin and take a sum, we will get 1. Because the relative, if you compute relative frequency for every bin and take a sum, you will get 1. It means 100% of the values, all values, right? Moreover, it will be 1 regardless how many bins you use and regardless how many values you have. So the density distribution is always invariant of the number of bins, and the number or area at least of the density distribution is constant, is always 1. And that makes the density distribution comparable. So we can compare a density distribution, for example, derived from different samples and derived from different sample size and different number of bins and so on and so forth. So this is just an example. So if you take area of every bar here and take a sum of these areas, the total area of the all bars in this distribution will be equal to 1. Okay. And as I said, it doesn't matter how many bins you use. Of course, the shape will be a little bit different because you kind of have more noise here, and then it's more like smoothed here, but the total area is always equal to 1. So if you compute area of any of this histogram, it will be always equal to 1. So that's important about the density distribution. What else is important? And you can also see the relation between these areas and the percentiles, right? Because what if you compute area only on the left side? So if you take this interval and compute area on the left side, that gives you exactly the percentile, right? So because if you compute this sum of these areas, it will be sum of these relative frequencies. And sum of the relative frequencies, it's cumulative relative frequency, or it's what we call a percentile, right? So in this case, for example, we can say that 48% of the values are smaller than 10.3. Okay. And if you make a plot, so in this case, I have a percentage plot for my sample size of 100. And if I use if I take 10.3 and see what's the percentage value of the 10.3, I will get exactly 0.84. It's area on the left. So now you can see a direct relationship between these two plots. What is just a value here, the percentage on the percentile plot, it's an area on the left here. It's an area on the left on the distribution, on the density distribution histogram. This is very important to remember. Okay, so now we know quite a lot about how to compute different frequencies, relative frequency counts, how we compute density. But all these computations are based on our sample. So all these computations are empirical. They are based on experimental results. Now let's talk about how we can generalize it and have some theory behind this. How these frequencies, the relative frequencies, the densities, and so on and so forth, relate to a very important thing in statistics, which is called probability.